this video, we'll begin our discussion of the normal random variable. Our file is normal.xlsx. So this is a continuous random variable. Can assume any value on an interval. And what are some things that follow a normal random variable? Well, height, weight, IQ, number of points an NBA team scores in a game. Let's say chocolate bars sold every day by a supermarket. We'll explain why that is in the next video. Let's say at Whole Foods. The daily return on a stock, percentage return, is often thought to be normal. It may not be, but a lot of finance people will model it, the daily percentage return on a stock as normal random variable. And so those are some examples. Okay. So basically, a continuous random variable has the possibility of assuming an infinite number of values. Like your height could be anything between, I don't know, 3 feet and 8 feet tall. The weight of a human being could be anything between 0 pounds and 400 pounds. I said 1 pound and 400 pounds. I don't know. Okay. But continuous random variables are characterized by a probability density function. And so I can actually draw this for the normal random variable. Let's do it for IQs. Now, to define a normal random variable, you need a mean and a standard deviation. So the mean IQ in the world is 100. The standard deviation is 15. Okay, you remember we talked about 68% of the time a data set's within one standard deviation of the mean, 95% of the time a data set's within 2 standard deviations of the mean. That basically comes from the bell curve or the normal random variable. Now, if there's a function in Excel to help you draw the probability density function, or PDF, for a normal random variable. It's NORM.DIST. You put in the value of, let's say, IQs. We could go 50 to 150. And then the mean is 100, sigma is 15, and you put the word false in. So if I would put IQs 50, 51 through 150, and basically the probability density function would be norm.dist, and I put in the value, I put in the mean, I put in the standard deviation, I put in the word false. Oops. Norm.dist. So that's what we, okay. So now if I would graph this, actually, let's put the mean in a separate cell and the standard deviation or sigma in a separate cell, because then I can vary these and you can see what goes on here. So I'm going to do this again here. So I'm going to replace the mean. I can hit F2 to edit this cell, and I'm going to make the mean be this cell, $sign it, and the standard deviation be this cell, right there, $sign it. Okay, now I can copy that down and I can get a normal density. Okay, so let's just graph this. I can do a scatter plot, insert right here. Okay, there's a normal density. Okay, so the mean is 100, standard deviation is 15. Let's move that up a bit. Okay. Now let's suppose I raise the mean. Let's first look at this. Okay. Where is the highest density? The height of the density indicates how much probability is around that value. So for an IQ of 100, the height of the density is highest at 100. So 100 is going to be the most likely IQ. And if you move down to basically, so the height at 100 is what? It's 0.02634. And if I look around 83, it's about half as high. So that would mean an IQ of 80, about half as many people have IQs near 83 as 100. Also, this density is symmetric. It looks the same to the left of the peak as the right of the peak. And total area under the density equals 1. And area under the density is probability. So you want to know the chance somebody has an IQ of 80 or less. You want to know the area to the left or equal to 80. And basically, the NORM.DIST function, when you change the false to true, will give you the area to the left of a given value. Okay, but you can see the density here is symmetric. It looks the same to the left of the peak as the right of the peak. In other words, if you have an IQ of 80 or 120, you go 20 below the highest, most likely IQ, and 20 above, the height is the same. Not every random continuous random variable has a density that's symmetric. Okay. So now we can try and answer some probability questions, okay? And again, the key would be to use the fact NORM.DIST, you give me a value of x, a mean, a sigma, and a true, gives the probability the random variable is less or equal to x. But before we do that, let's see what happens. Like if we raise the mean IQ, okay, what do you think will happen to this density? It should go where the peak is at 110. See, it did. The spread about the mean doesn't change much at all. Okay, but let's go back to 100. Suppose I make the standard deviation be 2. Well, then it's much tighter. Okay, almost nobody goes below 90 or above 110. If I make the standard deviation be 20, it's more spread out. Okay, see, it hasn't even dropped off yet. Okay. So let's answer some questions about IQs. In other words, the chance a person's IQ is within one standard deviation of the mean. That's 85 to 115. Well, basically you take the area to the left of 115 minus the area to the left of 85. So you can do a NORM.DIST. Okay, 115, the mean is 100. See, that's how many people have IQs less than or equal, what fraction of IQs less than or equal to 115. And I'll take away those people have IQs less than or equal to 85. That should be around 68%. That's within one standard deviation. So 68% of people have IQs within one standard deviation of the mean. Let's go within two standard deviation. Chance a person's IQ is between 70 and 130. We said that's about 95%. Well, we can check that. We could take NORM.DIST. What fraction of IQ is 130 or less? And take away all those people have IQs 70 or less. That should be around 95%, 95.4%. So 95% of people have IQs within two standard deviations of the mean. So when we talked about when we make predictions from regression, 95% of the time, the actual values within two standard errors of the prediction, we were saying in essence, the errors are normally distributed, okay, which usually turns out to be a good assumption, but you can check that if you want to. Okay, so now we can talk about finding percentiles of a normal random variable. there's a function for this, NORM.INVERSE. Okay, so in other words, I could find basically the 90th percentile, the 10th percentile, etc. So let's suppose we have income in a town, or let's suppose annual demand for a drug. Annual demand for a drug is normally distributed let's suppose the mean is 60,000 and the standard deviation is 5,000. Suppose it's pounds. If you want to have a 5% chance of running out of the drug, how much should you make? Well, that's the 95th percentile. In other words, you want the number with 95% to the left of it. In other words, if I would put a 60 and a 5 here, well, that's going to mess up our beautiful picture there. But basically, I can show you a normal random variable with a mean of 60 and a standard deviation of 5 using some add-in that we have that's a great add-in called at risk. Okay, so now if I can draw a little picture here. See, there's the mean of 60 and standard deviation of 5. And see, if I want what has 5% to the right of it, the 95th percentile, I mean, I can show you, there's a picture, 68.22. Now, don't worry about how I drew this picture. I'll paste this graph here. Well, we'll just use the fact that that's 68.222. It doesn't seem to want to let me paste the graph there. So I would say the 95th percentile. So I would say norm inverse and I'd say 95th percentile, the mean is 60, standard deviation 5, and there's the 68.22. Again, what that would look like, see there's 5% to the right of 68.22. Now, if I wanted to know the 10th percentile, okay, in other words, there's a 10% chance we will sell less than what amount? In other words, what number has 10% to the left of it? Okay, the answer would be 53.59. The 10th percentile, 10% chance we sell less than. Norm inverse 0.1 60, 5, and there's that 53.59, 53,000, again 592. Okay, so we can use the NORM.DIST to find probabilities. In other words, what's the chance IQ is greater than or equal to 130, for example? It's 1 minus the chance that somebody's IQ is less than 130. Again, that NORM.DIST function will do that. So to have 130, means 100, standard deviation 15, and basically it should be about 2.5%, I would think, 2.2%. Okay, because if you're going to have 5% more than two standard deviations from the mean, there should be 2.5% more than two standard deviations above the mean, and there should be 2.5% more than two standard deviations below the mean. And so that makes sense that we get about 2.5% there. Okay. In the next video, we'll show you why the normal random variable is so important due to something called the central limit theorem. Even if lots of things in the real world are not normally distributed, when you add them together, in all likelihood, you get a normal random variable. So we can calculate a lot of interesting probabilities if we understand the normal random variable. So we'll discuss that central limit theorem in the next video.
Okay, so thanks for watching, and there's a free course, a free 21-day course from Dr. Winston, and all of these videos are coming from one of three books. So first, this one, which you can see here at the top of the screen, Microsoft's book, which has 355 reviews, and then it's, let's see, 4.6 stars. It's coming from this book as well, his marketing analytics book, which is down here, and you can sort of see 4.5, or his newest book, his analytics stories book, which is here. And with that one, you can see it's 4 point something, or maybe even 5. I don't think it's 5. Yeah, 4.8. And so, yeah, anyways, in the description, there's a free 21-day course from Dr. Winston, or you can go to excelwithwayne.com/free, and it'll be there. But again, thanks for watching, and if you have any questions, just please let us know. Thanks.